Welcome to the modern view of atomic structure. Now, this is just an introduction to the modern view. So, currently, we know that the atom consists of a very, very tiny, very, very dense nucleus. And so that's there, that little sort of purple dot. And this nucleus contains most of the mass of the atom, and it contains protons, which are positively charged particles, and it contains neutrons, which are neutrally charged particles. So, again, it's really, really, really tiny. This drawing is not to scale. So, it contains, the atom consists of a nucleus containing the protons and neutrons, and it consists of electrons that are orbiting the nucleus in the electron cloud. Now, the paths of these orbits are not able to be predicted. Now, by orbiting, we don't really mean orbiting the nucleus in the way that planets orbit the sun. We mean they're moving around, but we can't predict the path of the orbits. Now, by can't predict, I don't mean we don't have good enough instruments, or we haven't yet figured out what the orbits look like. What I mean is it's not physically possible to predict the path that the electron is going to move on, because the electron is not just a particle. It acts like a wave. So, well, I don't want to get into it too much, but suffice to say that the electrons just exist in an electron cloud, right? They're out there around the nucleus somewhere, but they're not orbiting in fixed paths like the Earth orbiting the sun, right? They're moving around, but we can't say, given where the electron is at one point, we can't say where it will be at another point. And again, not just because we haven't progressed far enough scientifically, it's not possible. The universe doesn't even know where the electron is going to be in the next instant. It's just around the atom somewhere, around the nucleus. So I want to point out a little bit about the ridiculous tininess of the nucleus. The radius of the nucleus is about 100,000 times smaller than the radius of the atom. Now, that's the radius, or the diameter, but that means that the volume, because volume is the cube of the length, the radius, so that means that the volume of the nucleus is about 1/4,000,000th of the volume of the atom. That is ridiculously tiny. So this image of showing the nucleus there is not at all to scale. If it were to scale, then the width of that nucleus on the screen here would be 1 pixel for every 100,000 pixels that the electron cloud takes up. Well, width-wise, right? Not area-wise, but just length-wise. Now, the screen doesn't have anywhere near 100,000 pixels wide. It's roughly 1,000 pixels wide. So we wouldn't see, it wouldn't take up but 1% of 1 pixel across this screen. So it's really, really tiny. The nucleus is really, really small. Also note that this 1/4,000,000th of the volume means that if the nucleus was the size of a golf ball, an electron at the edge of the atom would be 1.5 miles away. Now, to put that in perspective, if the sun were the size of the golf ball, then the Earth would be 9 inches away. Now, the sun and the Earth are really far apart. There's a lot of empty space there, right? But what this means is that if the nucleus was that size, and the electron on the edge of the atom is 1.5 miles away, that means that there's way more empty space inside the atom than there is in space in the solar system. So there's way more empty space inside your body than there is in outer space. That's how crazy small the nucleus of an atom is. So So atoms are mostly empty space. There's that really, really tiny nucleus, which is really, really dense, and contains almost all the mass of the atom. And then out there, spread way, way far apart, are the electrons moving around. But they're so far apart from each other and from the nucleus. So most of the space there is just totally empty, with nothing in between. So, I want to talk a little bit about atomic number. So the number of protons in the nucleus determine which element the atom is. So if we have one proton in the nucleus, then it's a hydrogen atom. If we have 2 protons in the nucleus, we have a helium atom, and so on. Carbon has 6 protons in the nucleus, oxygen has 8, and so on. So atoms of a particular element all have the same number of protons in the nucleus. They may have different numbers of neutrons and different numbers of electrons, but they all have exactly the same number of protons, and if they don't, then they're not of that element. It's a different element. So the number of protons in the nucleus is called the atomic number. So the number of protons, or the atomic number, is enough to identify which element an atom is. Now, the mass number, or the atomic mass, is the sum of the number of protons and the number of neutrons. So if we have 6 protons and 6 neutrons, then the sum is 12. The mass is 12. If we have 6 protons and 7 neutrons, then the mass is 13. But both of those have the same number of protons, which means they're both carbon atoms. But one of them has a mass of 12, and one of them has a mass of 13. So these atoms of a particular element, carbon in this case, can have different numbers of neutrons. That means that they're different in a fundamental way, but they're also very, very similar because they have the same number of protons. And because they're both the same element, but they have different masses, we have to differentiate between them in some way. So we call them isotopes. Now isotopes have the same number of protons, but they have different atomic masses. So again, in this case, one has a mass of 12 and one has a mass of 13. Alright, now we need a way of denoting these isotopes, and so we use isotope notation. So here we have a big capital X, where X is the element symbol. Now, you'd actually use whatever the symbol was of the element. So in the case of carbon, it would be C. Then we have a capital A. A is the mass number, and Z is the atomic number. So if with our earlier example of the 2 different carbon isotopes, we would have a big capital C for each one. They each have an atomic number of 6. They have 6 protons, so we write a 6 down here in the lower left for each one. Now, they have different masses. So the first one would have a 12 on the upper left, and the second one would have a 13. Now, remember that these are the masses, not the number of neutrons. So to find the number of neutrons, you have to subtract the number of protons from the number of neutrons. So 12 minus 6, 6. So in this case, we have 6 protons, and 12 minus 6, or 6 neutrons. In this case, we have 6 protons, and 13 minus 6, or 7 neutrons. So we're not listing the number of neutrons, we're listing the mass, which is the sum of the protons and neutrons. And we're listing the atomic number. Now, yes, it is a little bit redundant to write both the atomic number and the symbol. So sometimes we just write the symbol and the mass. So we could write it that way, or we could write it this way. Right? Carbon 12 or carbon 13. Right? This is how we say these. So if we have a case like this, we say this as sodium 23. Remember, Na means sodium, so we say this as sodium 23. We don't say sodium 1123 or something like that. It's sodium 23 because saying sodium identifies which element it is. That automatically tells us how many protons it has, and then 23 tells us the mass. We can figure out that it has 12 neutrons from that point. So this is a sodium isotope with 11 protons and 12 neutrons, because 23 minus 11, of course, is 12. So this is the modern view of atomic structure, and it's just an introduction to it, just a little bit of the modern view.